This is also, a lot of this is being done by people in my team, people in other teams, people outside IBM. So this is definitely not one piece of work, and it's definitely not work that's already done and published or such, right? So this is active, ongoing work. So by the way, and please don't hesitate to ask questions during the talk. I'm happy to be interrupted. Makes it much more lively that way. So let me get started, right? So what am I going to talk about, right? So I'm going to first start with some of the broad trends in the cloud space. So what's happening in the industry? How are people adopting cloud? How we are moving to increasingly a hybrid and multi-cloud environment, and what are some of the trends that are making that transition right now. And we'll talk specifically about networking and some of the challenges that comes in networking because of adopting a hybrid and multi-cloud environment. We'll talk about observability and some ways in which we can leverage observability for intelligent network management. So that's the overall agenda. So, oops.
Can you move them somewhere down? Thanks.
Okay. So this chart here talks about how the cloud market is evolving. Right? Going back about 4-5 years, you will see that largely it was the hyperscalers, right? So Amazon, Google, Microsoft, that were owning a lot of the infrastructure that was being deployed in cloud. Increasingly, that is shifting where the next set of companies are growing much faster than the hyperscalers. Right? So that's also because there are a lot of specialized vendors that are bringing in niche infrastructure. This might be infrastructure for, let's say, AI-based workloads, or infrastructure in a specific geography where data may not be able to take the data out of that geography, and then they're providing data centers right there. So a lot of those trends, and I'll talk about edge computing also, which is driving some of these trends, where increasingly there are a larger number of cloud infrastructure providers, and deployments at edge and deployments outside of your large data centers are becoming increasingly prevalent. So the companies like, for instance, Cloudflare and Bridge, you will see from this chart, right? So the red are really the hyperscalers. They are in a very limited set of locations. Yes, they have very large data centers, but if you look at the purple and the blue, there are so many more data centers. They may be smaller in size, they may be specialized for certain kinds of workloads, but they are really being ramped up across a large number of cities worldwide, and large cities and countries. So this expansion is growing like 100 times, right? Whereas the traditional cloud data centers are growing, but not at the same pace. Right? One of the big trends that is driving this evolution is edge computing. So increasingly, people are realizing that you need to deploy compute closer to where the data is being generated. And where the data is being generated is in this sort of industrial applications or retail or telco, and increasingly drones and connected vehicles and so on, right? So that's where increasingly that's where the data is being generated, and that's where compute is migrating towards. And what is happening is the hyperscalers are approaching edge computing from one direction, right? So they are expanding their public cloud services over to the edge, right? So they will provide same sort of public cloud services available in an edge data center as well. But typically, they will only permit you to deploy the same services that are available in their own public cloud, not in a competitor's public cloud, or bring your own sort of infrastructure or software. Now, the other way in which this is being attacked is from the telcos. So telcos already have a large deployment. So you have your 5G. Actually, I have the next slide on 5G. Yes. So what is happening with 5G is we are moving towards a spectrum that permits like ultra low latency. So it's like order of magnitude lower latency for communication. And it also is like an order of magnitude higher bandwidth, permits higher density of devices to be connected simultaneously. And all of this is also permitting compute to be run closer to the edge. So the telcos with their 5G towers, you now have compute that is available very close to the end users. So within, when you're in an urban setting, within like 100-meter radius or a few 100-meter radius maximum, you're close to a tower. And that tower can actually hold a few servers and can run compute there. And increasingly, this is also being deployed in private settings where a specific educational institution or a factory or a hospital can deploy their own compute infrastructure close to your cell towers, close to your 5G infrastructure. So it runs parallelly and you can reach your internet much quicker. You can reach your compute infrastructure much quicker. And that is again bringing a lot of compute from your traditional data centers onto these sort of edge locations. Now, with all of this, now what is increasingly happening, as you would imagine, is data is massively distributed. You no longer need to copy over all of your data into one location to then process this data. So data is distributed and it's naturally distributed, and we want it to stay that way because it's expensive to copy that data over, or there may be regulations that prevent you from doing so. Applications, therefore, are moving closer to the data, and therefore applications are also massively distributed. And of course, the user base, all of us across the world, are also massively distributed. So all of that put together is pushing enterprises to deploy their applications in a geo-distributed environment across public cloud, private cloud, edge data centers, and so on. Right? So no longer is your application running in one cluster or one VPC or one VM. Right? You are increasingly running this across few, or maybe in the single digit for some of these enterprises, but enterprises starting to adopt Edge are seeing this move to hundreds of clusters. So now, how do you then manage these sort of hundreds of clusters that are geo-distributed in its deployment? How do you then manage it? How do you provide the networking capabilities? And that is becoming an important issue. It's just solving the connectivity challenge. How do you do it in a simple, secure, automated manner is becoming a huge challenge. And how do you then manage that network? How do you then manage that compute across this geo-distributed environment? Is the big evolution that is happening in the cloud marketplace today. Okay? And that background is around which a lot of the work in the team that I lead happens in IBM Research in India, and also in several other teams globally in IBM Research. So this picture tries to capture this. Right? So we are operating across infrastructure deployed across public, private, edge clusters. So your applications are distributed, data is distributed. And what we want to do is support all of your compute capabilities around. So we want to be able to help enterprises modernize their infrastructure to adopt this new modernized infrastructure, cloud native infrastructure. We want to enable testing and verification of software that is geo-distributed in nature. How do you provide security and compliance, both for your code as well as even your infrastructure is now deployed as code. So how do you manage security and compliance? How do you do distributed data management? That's a core area of work. And the focus of this talk is going to be around networking, and specifically I'll talk about application-aware networking and what we mean by that. And how observability and AI ops ties in nicely with the multi-cloud networking. Coming to just highlighting some of the challenges, right? So now that we are in this sort of hybrid multi-cloud world where applications are deployed across heterogeneous sort of clusters, right? You might have some of these maybe Kubernetes clusters, some of these may be running on VMs, some of these may be bare metals or Docker containers, right? So regardless of the nature of the infrastructure, nature of the platform, and regardless of where this is deployed, whether it's a public cloud, private cloud, edge cloud, right? How do you now manage all of these different application environments, this infrastructure, in a seamless manner? So typically for the enterprise, they want a single way in which they are able to manage all of these heterogeneous resources and infrastructure, all of the applications in this geo-distributed environment. And today, that sort of thing is missing. And if you take it to one extra level, right? So if you look at electricity in this room, all we cared about when we walked into this room is you found a switch and you were able to turn it on and you were able to get the light we needed. If you needed more light, you will turn on another switch, right? That's all you cared about. You really didn't care about where the electricity came from, who did the plumbing to do the wiring for this, right? How did all of that come about? In the cloud world also, we want the same sort of utility computing. It shouldn't matter where the infrastructure is coming from. It shouldn't matter who is providing that infrastructure, where it is running, and so on. All you care about is your business logic should run, right? Your analytics workloads or whatever is your compute that they should run, and they should provide the right level of security, performance, reliability that you care about. Everything below that layer is something that the end users should not have to worry about. And that is when we'll get true utility computing in the cloud sense, right? And that's kind of how we defined cloud 60 years back, and we're still not at that point. So what we are driving towards is really that sort of a vision, where regardless of the heterogeneity in the infrastructure, regardless of where the applications are running, we provide that seamless, unified experience to the end application developers or your DevOps personas who will be able to manage this infrastructure at scale. Right? So that includes managing the compute, storage, network, managing observability of like how do you figure out if there are problems in the infrastructure or your applications, and how do you learn from those and rectify those. Right? So those are the sort of challenges that broadly we are working on. Okay, and what is also largely true today is that the compute automation is growing at a much faster pace of adoption than really network automation. So what I mean by that is today, or maybe 10, 15 years back, you would go to an environment, you would manually deploy your application there. Increasingly, that is being automated. So you can just specify where your infrastructure is, and you can write Ansible or other sorts of automation code to automatically deploy your compute infrastructure, your compute set of applications. And you can also set up policies to dynamically adapt this. So you can have an auto-scaling policy, you can have a policy that will automatically restart your applications if there is a failure. You can even automate things like failure detection and remediation and so on. Right? So that part of it, automating and dynamically adapting to different loads, adapting to different failures in the system, all of that on the compute side has been largely automated, and people are able to handle it. However, the same sort of agility does not exist in the networking world. So if you want to be able to manage applications that are auto-scaling, that are dynamically connecting to a large number of other applications that are geo-distributed in nature, so these connections are coming up and torn down dynamically. So those sort of things are kind of very hard to do. It involves understanding things like which subnet am I on, what sort of tunnels do I need, what ports do I open in my firewall. A lot of those aspects are still manual in nature. Right? Yes, there is some level of automation, some scripting that exists, but to a large extent, that network automation in a multi-cloud heterogeneous environment does not exist today. Going through how the networking itself has evolved, right? This might also throw a bit of light into why the compute has been faster than the networking in terms of automation. So around the I think 2005-2010 timeframe is when SDN became popular. Software-defined networking. I'm not going to go into details of that, where you're able to separate out the control plane from the data plane. So that became popular in a data center environment. And in the next generation, around 2015 or so, SD-WANs became popular. So this is software-defined wide area networking. So even when you are connecting to applications that are geo-distributed, are sitting in a different cloud or a different cluster outside of your on-prem data center, you can still use software-defined networking principles to connect to them. So this involves creating encrypted overlays, managing different subnets and IP address ranges, and so on. This was again largely, I think, automated, but what it enabled was typically cluster-to-cluster connectivity. I can enable my on-prem data center to connect to a public cloud environment, but it would mean that my entire pipe is now open. Any application here would be able to talk to any other application there. Now, increasingly, what's happening in a hybrid multi-cloud SDN is it's not just enough if I open up my entire data center to a remote data center, to a public data center, for instance. I actually want to specify fine-grained policies of which applications, which connections I want to permit, and only permit those connections. Anything else will be dropped because of policy. And I also want to specify some of the higher layer constructs or what an application developer or a DevOps person would care about. I care about security, reliability, performance. Can I just specify those as requirements? So I could say I'm interested in 300 millisecond latency for my connection. I don't really care how the networking is set up. Right? You take care of the networking. So that sort of abstractions don't exist today. And I'm moving towards what I mean by application aware networking or application oriented networking. I'll get to that in a couple of slides. Again, a little bit of background on again the networking evolution itself. Alongside software-defined networking and SD-WAN sort of principles, we had Kubernetes itself being adopted as pretty much a standardized platform for cloud-native development. I hope many of you are aware of what Kubernetes is. But in terms of networking, what Kubernetes provides is actually very, very simplistic. It has a very flat network. It permits every pod, every container in your cluster to talk to every other container through what is called a container network interface, a CNI. There is a standard CNI specification, but there are many, many different implementations of the CNI. Cilium is one such container network interface that provides IP address management and connectivity for your containers. But all of this is still within a cluster. So this is the networking that happens within your cluster where one application in the cluster needs to talk to another application within the same cluster. So that is handled by Kubernetes networking with a very kind of flat topology. Now, alongside that, service meshes came along around the 2015-2017 timeframe. Istio is a very popular service mesh. This provided a lot of the layer 7 connectivity requirements where you're only specifying things at the application layer, not really working at the layer 3 or the IP layer. And so here, service meshes, they connect microservices typically by running a sidecar alongside your container. And now that is also there's some changes going on there as well. You may have heard about ambient mesh, where instead of having one sidecar container per pod, you have just one proxy container for the entire node in the cluster. So every node will run a proxy, and you will provide your networking through that proxy. So there's a lot of innovations that are going on in the single cluster mesh sort of solutions even today, and that's where some of these layer 7 proxies come about, right? So instead of having a layer 3 gateway that provides IP layer connectivity, you're starting to talk about layer 4 and layer 7 proxies. But when you're coming to multi-cluster networking, that is a whole altogether new, different ballgame, and there are no really standard solutions. There are some solutions that help you connect different Kubernetes clusters together, but they kind of they fall short when you want to connect different heterogeneous environments. So I want to connect a VM-based environment to a Docker-based, container-based environment to a Kubernetes sort of environment. There is still they don't work all that well. There's a lot of active work and a lot of startups in this space also working towards this sort of how do you provide network connectivity across a multi-cluster, multi-cloud environment. But providing that sort of integrated solution and application centricity, I'll come to that application centricity, it doesn't exist. So what do I really mean by application-centric networking? Right? So this goes back to what I talked about in terms of the utility model for cloud computing. Right? I typically, as a cloud developer, I care about where my applications are being deployed, which other applications I need to connect to, what is the security, performance, reliability requirements. So that's what they're going to be specified. And underneath there may be a lot of dynamicity. Right? So the applications may need to be migrated around, they may need to be restarted, scaled up, scaled down, and so on. All of that needs to be managed and still provide the same level of reliability, performance, and security that you care about. And it shouldn't matter whether these applications are running on cloud, edge, on-prem sort of environments. And I still want that unified experience. I still want to be able to have a dashboard where I see where my applications are, how they are connected, how they are performing, whether there are any security issues and so on. Right? So that sort of single view is something that any application developer would be interested in this sort of environment. Now, how does that translate into networking requirements? So what this means is that I need to be able to translate your connectivity requirements into policies. So I need to be able to say that I only want to permit my inventory application to talk to my web service application. Right? I don't want any other connections to be allowed. And that inventory application may be running in a VM somewhere, maybe running in a Kubernetes cluster somewhere else. Internally, they should get translated into either layer 3 policies or layer 7 policies, as the case may be, depending on how your networking solution is set up. And all solutions are possible in every layer, and there is a lot of work that's going on in every layer of the stack in terms of providing these sort of connectivity. And there may be other sort of policies that you need in terms of security policies, performance policies, QoS, and so on. Again, this should be immaterial to where the infrastructure is. So from an application standpoint, I would just specify I need 300 millisecond latency, or I might specify I want always two alternate paths through my overlay network or even my underlay network. And the networking should take that up and provide the right sort of, let's say, load balancing rules or my HA rules, right, high availability rules, and provide that sort of network connectivity that is needed. So how do you do that translation? So first, there is a specification of the application. So application needs a uniform way of specifying this that is independent of the infrastructure, regardless of whether this is VMs, containers, or so on. There should be a uniform specification, and there should be a translation layer that takes that specification and converts that into a set of policies that can be implemented in the network. And those policies may be different if it's a layer 3 solution versus a layer 4 or layer 7 solution. So this is, I think I covered most of this. Right? So what we are driving towards is this vision where you have gateways running close to where the applications are deployed, and this is immaterial of where the applications are running, whether it is IBM Cloud, AWS, on-prem, edge cluster, it shouldn't matter. We'll run this sort of a gateway close to your applications, and we'll create an overlay that connects all of these gateways together. So the gateways are doing a lot of the heavy lifting. They're providing the data path connectivity, they're doing the policy enforcement, they also have to provide the right level of reliability, performance, and so on. So there is a central management hub. So that will be the uniform way of visualizing how my enterprise network is looking like. Where are my applications? Which applications are talking to which other applications? What is my level of performance? Are there any faults in the system? Is there network congestion? All of that is visualized through the management hub, and that's also the interface through which you specify your requirements from an application standpoint. So that's where the management hub, what you're specifying there, gets translated into networking constructs that get implemented in the data plane, in the gateways. And we are providing unified abstractions across different infrastructure. We are also making standardized APIs and so on, as well as providing the right level of performance, reliability, and security. So going beyond this, right? So some of the more research challenges that we are looking at right now is starting to look at application-aware traffic engineering. So given that I have certain QoS requirements, how do I need to manage, let's say, congestion within the network? So maybe one sort of problem that I can describe is, for instance, for an enterprise, I might, for a specific, let's say, connection, this might be a connection where I really care about latency, right? I want to minimize latency for that particular connection. That gets translated into a traffic engineering policy at the lower layer. Instead, there may be, let's say, a CTO of a company who wants to minimize the overall cost of network connections across the enterprise footprint, and they might have a different set of policies ongoing, right? So where there they might have different load balancing policies and so on. So how do you provide for these sort of traffic engineering principles to be applied with application requirements in mind? And one of the challenges there is these application requirements need to be trickled down to the networking layer. So for instance, in your TCP or your IP packet, you need to be able to tag saying, this is the sort of application and I need to treat this differently in my data. So those are the sort of challenges that we are looking at today. There's also longer term challenges around capacity planning. So a lot of these applications are highly dynamic in nature, right? So especially moving towards edge, right? Today I might be operating with 10 edge clusters. I know that I want to scale to 100 edge clusters, let's say in a year. How do I plan my network even before I start deploying to those 100 different sites? Invariably, what's happening today is people deploy onto the 100 sites, right? And then start thinking about the networking. Rarely works well that way. If you're able to plan ahead and cater to your growing demand, then the networking can work hand in hand with your infrastructure and computing requirements. So those are sort of problems that we are looking at. And finally, the other problem that we are faced with is also that now the networking, compute, applications are all distributed in nature. Your observability of how you are monitoring the system, right? So this could be metrics, logs, traces that you're collecting from the system. They are also being collected at the edge of the world, right? So each of these gateways running in a geo-distributed environment is constantly monitoring metrics, is collecting logs, is collecting events, like failure events, and so on. So now this observability data is massively distributed. How do you then derive insights from this geo-distributed data and still be able to do some of your traffic engineering, network optimization, congestion avoidance, and so on? So all of the work in the past has worked with the assumption that all of the data needed for congestion avoidance or load balancing, like efficient load balancing, all of that data is available in one place. But today that's not true, right? The data needed for some of these algorithms in terms of network planning, optimization is also distributed in nature. So those algorithms also need to evolve to allow for being able to process across distributed data. So I'll pause here before I go to a few other things. We'll provide a little more details in case there are any questions. Let me also see how I'm doing on time.
So,
yes.
In all these approaches, I see that there is very little information exchange between the consumer or the user and the service provider. So, for example, if you want to do any load balancing or performance optimization or traffic engineering, you need to know about the network state or both sides have to know about each other. Similarly, about meeting latency for computation, you need to have some kind of idea about the scheduler, or at least you should be able to influence the scheduler.
In this, we do have that, right? So here we are managing the network. We are getting a set of requirements from the application layer, right? Translating that into network policies, but we control the network. So we are able to get all of the current state of the network through metrics, traces, any of the information that you need, we are able to collect now. We are able to get events. Let's say there are failures in the network, we get that information. But
for that to happen, you need to have the same entity managing both the infrastructure as well as the consumer, the application, right?
Not so. Yes. So even the infrastructure, right? So we can have our agents running in the infrastructure to collect, let's say, CPU memory of the applications and so on, right? So you can certainly collect. So none of wherever you're deployed, right? Whether it's an on-prem or a public cloud, you can still get metrics pertaining to your infrastructure, your compute resources, storage, your application layer, KPIs. You can get all of those metrics, and you can also get network metrics together. So that's actually a big trend today, right? So combining infrastructure, application monitoring together with network monitoring for deep insights, right? So that world, those two used to be completely different worlds, right? So the network engineers would never talk to the application engineers; they were completely segregated. But now all of that is coming together, and we are getting to this world of full stack observability, right? Right from hardware monitoring to platform monitoring, like the Kubernetes layer, you can monitor CPU, memory, cache, and so on. And then you can monitor at the application layer, right? How many requests I'm processing per second, how many databases, JSON database access, how much am I reading, and so on. So all of that, so you can get the application metrics and you can get network metrics also. So all of that we are able to collect and analyze.
So are these metrics available at the overlay level or at the underlay? Because
yes, that's a good question, right? So the underlay may still be managed by a specific provider, and we may not have too much visibility into the underlay. Most of this is at the overlay that we are constructing. Right? But there are actually startups. I think there's one called Packet Fabric, if I'm not mistaken. They actually bring their own underlay. So they have constructed an underlay across across the major continents. They've set up the fiber and such. They provide the underlay and then they provide an overlay solution on top. So then you have the advantage of having access to both the overlay and the underlay. And likewise, if you are operating within an on-prem environment, then that enterprise has access to the underlay within that data center. So they can do certain optimization, but that will be limited in nature because it's only that environment, that on-prem environment.
So are we moving towards a kind of setup where you have more intelligence at the end host, that is like almost at the edge and not in the core?
That's certainly the trend that's happening, right? So intelligence is increasingly moving closer to the edge, but that does not mean the core is unaware of things, right? So what might be happening is the edge may be analyzing for let's say some congestion, or it might be analyzing for let's say a load balancing that it can do, but it might still communicate that insight back to the core, right? So the central intelligence might still be concentrated at the hub, but you might have intelligence on each of these sites, and there may be some coordination across those sites so that overall you have certain things that you're able to optimize. So I think that distribution of intelligence, or the decentralization of intelligence, is certainly a trend that's happening. Yeah. Because it's increasingly becoming infeasible or too costly to bring all of that intelligence to one place. That again amounts to copying all of that data to one central location. Instead, moving the compute closer to where the data is getting generated, that is cheaper, faster. You're able to respond to events or any problems quicker. You don't incur the much like several hundred millisecond latency to go back to the hub, process it, and then come back. Right? Instead, if you're processing right at the edge, it's faster, cheaper to do it that way. But then it's more costly in terms of management, because you need to manage so many sites. Intelligence is distributed. That unified experience is not there right now. So those are the sort of problems we are trying to solve, where management is also made easy, despite the fact that things are distributed. Okay, moving on, right? So I just want to highlight some of the work that we are doing in this space, and then I'll move on to some of the work we are doing in observability. So we're working with folks in Berkeley and also several other academic institutions in trying to build out this sort of what is being. There's a nice article, a position paper that was written, description in the slide. That talks about an extensible internet, right? So how do you, instead of building increasingly many overlays one on top of the other, can we actually bring in a layer in the networking stack itself that can handle some of these requirements coming in from the application? So there's a service layer that is being introduced above layer 3. This might get merged into layer 4 at some level, right? It might not be an independent layer of its own, but bringing in some of those capabilities so that application knowledge is available when you're looking at your layer 4 packet. Maybe this gets done in layer 7. So that's still being worked out, but not at the layer 3 level. Layer 3 is too low for you to start looking at application specific requirements. Right? So that's an active collaboration that is going on. And more broadly, our vision is to build this sort of open cross-cloud networking fabric. This is programmable, so people can bring in their own sort of components into this architecture. It's open and extensible, and it's operating above layer 3. So it's operating at the TCP layer or higher. And what we are doing is bringing this notion of a multi-cloud broader gateway that is extensible. So it comes with a certain set of capabilities to begin with, but you can bring in your own capabilities and deploy it into the gateway. And that the set of capabilities you bring can be fine-tuned for the set of applications you care about. So let's say this multi-cloud border gateway is deployed at an edge location. You can bring in network services that are fine-tuned for the set of applications deployed at that edge location. So that's the sort of extensible programmable fabric that we are looking to build here. We are trying to build this in open source. So I think we'll put this out fairly soon. Just a quick sense of what this looks like, right? So there is there's a controlled and private global application connection. So this is from one application to another application. So this is just not connecting one cluster to another cluster. This is connecting specific applications across. And we try to be as close to the application as possible. So the gateway may be running in the cluster. Let's say there's a Kubernetes cluster, it might run as another pod, uses a space pod in the cluster itself. So it has some knowledge that it's able to gather about what that application is. So there's some application knowledge that the gateway is able to receive, and then it will handle the control plane and data plane requirements. Again, here we are agnostic of layer 3 and below. So whatever is the underlying connectivity, we are not really looking at how the underlay is set up or whether it's going over the public internet. We are operating at above the layer 3. Right? And this is also something that is dynamically set up. So as and when new connections are started is when the control plane will determine how to connect these how to connect these applications together. It's not a static connection like how it used to be in the SD part. We are trying to do this in a much more dynamic. And some of these gateways are also implementing application level policies. So you could have, let's say, a load balancing policy or a policy that says only the application on the right can connect to this other cluster, this application running on this other cluster, but the application on the left here in the picture shouldn't be allowed. So that application will get dropped through a policy in the gateway. And what we are also getting towards is bringing in the notion of application identities. So there will be identities that are attested by the application itself. So we're using open source projects to do that sort of attestation. And that application identity will be verified at the gateway to enforce the policy. So this is all done at the application layer. So let me just pause in case there are any questions. Moving over to observability after this, and spend a bit of time on some of the challenges there and what we are doing in that space. Okay, if there are no questions, moving on. So starting at the level of a single cluster, right? So now what we are doing is we are leveraging this technology called eBPF, which is a new technology in the Linux kernel that started around the 2014 timeframe. Where your kernel is now becoming increasingly programmable. So in specific hook points in the kernel, you can actually attach your own code and you do specific functionality there. You can do that for efficient network processing, you can do that for security related use cases, and we're also using it for observability. So you can get a lot of deep metrics and insights on exactly how the kernel is processing both from a compute as well as from network. So there is a CNI that we tried to build that's available in open source for edge related. So it's a very simple CNI that can run on a Kubernetes cluster at the edge. And we are also using eBPF for network observability. So it actually helps reduce by an order of magnitude the overhead of collecting metrics. So this could be both in-cluster metrics, right? Whether it's collecting things like number of packets being processed by the gateway every second, or number of connections, and so on. So getting that information is extremely cheap, and you can also get things like latency. So I can look at TCP packets. Whenever a new connection is being set up, I can see the connection setup time or the round trip time across clusters, and I can also collect that very efficiently. So again, this is things that are built in open source, and some of this is now available as part of OpenShift, which is Red Hat's product based on Kubernetes. It's the open source product that Red Hat has. It's a Kubernetes environment, and some of these capabilities are available out of the box on OpenShift. Right? And yeah, the links are available. I would encourage you to take a look, and we've written some blog articles in this space. And we're also increasing the other sort of problems we are exploring is also things like distributed debugging and tracing. Right? So it's not something that we've worked on yet, but just calling it out as a challenge. Right? So when your application is traversing, your application connection is traversing multiple hops across clusters, how do I then trace where packets are flowing and get a distributed trace? Right? So if you have eBPF-based agents in each of these different gateways that are processing a packet, then I can get a distributed trace that will help me in debugging. So those are certain things that we are working jointly with academic partners. Yeah.
Question.
Yes.
Can you go back to the
Yes.
slides? Yeah. So in this, how scalable is it to use the hooks at a lower down the stack, like at a packet level, rather than a system call API or the socket request level?
Actually, much more scalable than the traditional networking, than traditional kernel-based techniques, right? So we've seen like an order of magnitude improvement if you are, let's say, just doing, let's say, a flow capture using kernel-based tools versus doing the same thing with an eBPF-based agent, right? Just because we are able to bypass a lot of the complexities of the kernel, over time the kernel has become a lot more complex. You can do this much more efficiently with eBPF. You actually mentioned something else which I wanted to say something and then lost my train of thought. But yes, it is an order of magnitude more efficient with and without eBPF, right? And increasingly people are moving to adopt this technology.
And the second question is, in a multi-tenant environment, how do you think this kind of exposing the UPF to the tenants?
Correct. That's a good question. Right now, all of our gateways are single tenant. But let's say you have a shared cluster with multiple tenants, then that may be a thing that we need permission to do, right? So we'll have to get permission from, let's say, the owner, right? So this might be the AWS or someone, right, to do this in a multi-tenant environment. But so far we're focused on enterprise environments, which are typically the non-shared type of environments, right? So each gateway is running for a single tenant, and there we are able to extract a lot of the compute networking sort of metrics.
Or if you have a VM,
This works as well. So anywhere where there's a Linux kernel, it works, right? So whether it's a VM or a container-based environment, it really does the same technology.
in a container, then you need support from the base.
Correct. The kernel already supports this, right? So we can get fine-grained metrics for every container. I think you mentioned system calls also.
Right.
So system calls is also a hook point that's available with eBPF, right? So it's a kernel hook point, and you can inject code there. You can actually track exactly what system calls system calls are being invoked, and you can also just program it for tracking specific system calls. So if I'm only interested in file reads and writes, you can track that with eBPF fairly efficiently, right? So even for system calls, and thanks for bringing that up. Right? So that's also something that's fairly efficient with eBPF.
And there you have more context available. Right?
Yes, because we are at the kernel layer, we have a lot of context, right? We're not in the user space here. So kernel layer, we get a lot of context about exactly what's going on, right? And we can map that back to. There's some work also that maps some of these lower level constructs to the nature of the application. So if there's a video sort of application, you know this is the sort of system calls it's going to invoke. This sort of network behavior, whether it's a video application or it's a chatty microservice sort of application, right? So just from the networking behavior or from the underlying set of characteristics, you can actually deduce what the application is trying to do. So those sort of, that's also an active area of research, right? So without, the application is a black box, but I can learn what the application is trying to do, whether the application cares about high bandwidth or low latency. I can actually infer by just looking at the underlying metrics. Okay, so 10 more minutes. Okay. So I talked about the single cluster domain and some of the work we're doing in terms of observing from a single cluster. Now we are expanding that to a multi-cloud environment. So we have multiple of these clusters, all of them generating metrics, all of them generating flow logs, events, and so on. Now what we are trying to do across a multi-cloud environment is looking at enriching these metrics with application-specific characteristics. So I talked about the management hub. So the management hub has knowledge about where these applications are running. This might also have certain labels on the applications because these are deployments that it's dealing with. It might know that this is a web server, it might know this is a database, or even at a business logic level, right? So this is an inventory application versus this is an analytics application and so on, right? We might have that knowledge, we actually have that knowledge looking at just the labels of these application deployments. We can tag that to the metrics we are getting. So if that particular application is running in a Kubernetes namespace on a particular pod, it is initiating a bunch of connections. So those flows, those connections, the metrics we are deriving from them, we are tagging it back with the application layer information that we have. And so we will know, we can tag it with saying, okay, this application was deployed by this user in this cluster. There are 4 other instances of this application running across the world. So all of that enrichment is now available to us. And that can help provide an interface to the end users in a context that they understand. So they no longer need to look at observability data query for a particular IP address and say, hey, what's happening with this IP address? They can actually ask a question, what is happening with this application with a name that says, okay, this is inventory app or something like that, right? So they can actually query based on that rather than querying based on a subnet or an IP address or a specific flow at the networking layer. So that is a huge abstraction benefit that we are hoping to provide, right? So where you no longer have to, the application developer does not have to care about the underlying network. They can talk in terms of like the terms that they understand, which is application name, cluster name, and so on. They don't need to worry about subnet, IP address, and such. Okay, moving on. I think these are, so there are some challenges around collection of this data across geo-distributed environments. Some of the research we are doing is also around what is the right level of data that we want to collect. We don't want to copy all of the raw data. I think I mentioned this before. Copying all of the raw data to a central site is just infeasible, too costly. What is the right level of aggregation, filtering, maybe even at the level of insights that we do at the edge before you transmit that to the cloud? So that's an important focus area in terms of research. I think I'll skip this in the interest of time. So this is kind of what it looks like, right? So you have IP address in there, but you have things like app name and such in your metric itself, and you can now query based on those labels rather than the networking labels. Now I'll just touch upon AI ops. So now that we have this rich source of data, which is metrics, logs, events, what we then want to do is have intelligence that looks at problems in the network. Diagnosis, starting with diagnosis, but then going forward to look at what is the root cause of the problem, right? And also what is the action that I can take to remediate the problem. So a diagnosis could be there's a congestion in the network. A root cause could be there's a gateway that failed that caused a lot more traffic to go through a particular region in the network, and that's what is causing congestion. That's the root cause is that gateway failure, and a remediation action could be either to reroute some of that traffic through an alternate path, or to spawn a new gateway and so on, right? So, or maybe optimize the placement of some of these gateways. So, taking this through the end-to-end spectrum of lifecycle management, right from collection of data to diagnosis to even predictive analytics and then remediation is something that we are working. I will also skip this, right? So there's a lot of different things that we need to do, right? So one of the challenges is also that there's a lot of data from different modalities, from different clusters. So just because there is an anomaly that is detected does not mean that there may actually be 10 different anomalies all pointing to the same root cause. So I need to be able to understand that although they are coming from different clusters, all of these problems are being reported from different points in my network. They may actually be because of one root cause that's causing all of that. So being able to put that together, grouping all of those anomalies together to derive insights from it, and also grouping these anomalies across metric analysis, log analysis, and so on, right? Across different different modalities of data we are collecting. That's also a challenge that we are looking at. So typically, a lot of the analytics that exists today is focused on a single modality. I can just do metric time series analysis. I can understand what's going on, or I can just analyze logs and see whether there are problems in the network. But combining the insights across these different modalities is still largely open. There's still some work in the last few years, but there's some open area of investigation. So I'll stop there. I think I'm almost running out of time also. So any last questions, I'm happy to take.
Hi, Praveen.
Yeah.
I'm actually asking you over Zoom. Am I audible?
Yes, you are audible.
Thank you. So basically, my question is around this, right? If you were tying a system call that probably spiked this CPU beyond a particular threshold, right? That is pretty much not deterministic because the spike for the CPU could have been from something else as well, right? So how would you tie that back to maybe a single application layer API call? So this because we can very deterministically track the observability for application layer, load balancer layer as an event-based system. But when the infra metrics come in, the non-determinism would come in, right? So how would you actually tie it?
Yes. So there are standard techniques. I don't know if I got your question right. Let me try to answer and then you can tell me if I got it right. So there are standard techniques like even being able to do like rolling window averages within inside the eBPF code itself to be able to handle some of these. And definitely with sort of infra metrics and even with latency, you will see some spike, right? Suddenly one packet will be slow or like one call may take a large amount of time. Typically we are not extracting metrics at that granularity. We will be extracting metrics at slightly aggregated granularities. This could be of the order of hundreds of milliseconds or seconds even. Right? Is that what you are referring to? So it's not like we are tracking every spike in the system and reporting that back.
Yeah, that's pretty much what I was asking.
So yes, I think there are. So going back to, I think it touches upon a larger point as well, right? So then you can do anomaly detection, right? There are anomaly detection ideally should not be based on a single spike, right? But let's say whatever algorithm you had to detect an anomaly, it is always possible that that anomaly is a false positive, or that anomaly and 100 other anomalies are all pointing to the same fault. So there has to be downstream analytics that take that sort of either threshold based or trend based analysis and then bring that together, have grouping and summarization techniques to then be able to understand what is the root cause of the problem. I think I don't think there's a way to get around that at all. What we are shooting for is increasingly more and more of that analytics to run closer to the edge so that you can respond faster. And I think that's what we are driving for. We are not trying to reduce the analytics that needs to be done. That is not a focus. Does that make sense?
Yes, thanks.
Okay. Yeah. Any other questions?
Maybe I will ask.
Sure.
So we didn't touch upon the you mentioned signaling and messaging protocols. So because all this, although things are possible, say for example within Kubernetes cluster there are protocols to share the information then outside, but then outside Kubernetes then you don't have any visibility. And Kubernetes telemetry will not talk to the network telemetry or even your other VM-based telemetry. So are there any efforts to standardize or at least enable interoperability
of telemetry information.
Telemetry as well as the control.
Yes, actually, that actually goes back to the slide I kind of skipped. So there is this open network called Open Telemetry that tries to bring in standardization across different telemetry modalities, right? Not just across different types of metrics, right? Compute metrics, network metrics, and so on. But it also tries to bring in standardization across metrics and logs, for instance, so that you're able to, for instance, combine information from logs together with information from metrics and create like a tabularized representation of it. And all of your downstream analytics can be then run on that tabularized representation. So Open Telemetry is trying to come up with those sort of standardization across telemetry sources. And Prometheus is a well-known open source project that ties in closely with, they are compatible with Open Telemetry. And we are actually leveraging Prometheus. So with Prometheus, we are getting the compute-related metrics, we are getting the network-related metrics. Some of our eBPF agents are also exposing metrics in a Prometheus format. So Prometheus is now that agent that will scrape metrics from different sources, whether it's compute, network, storage, hardware, and so on. And then there's this Prometheus agents running across the world, across all of these gateways. And we have another open source project called Thanos. So Thanos allows you to run Prometheus in a federated sort of environment. So multiple Prometheus instances can be running in a geo-distributed setting. And Thanos will take care of collecting all of those metrics and if necessary also federating queries back. So you can have a query sent to Thanos. Thanos will figure out which cluster or which gateway, which Prometheus instance has this data, and it will get that query back to you. It also does some level of compression of the data, collecting from different Prometheus instances. It has long-term storage capabilities, archival, and so on. And there is also a Red Hat project called Observability that handles things like role-based access control. So you don't want to provide data, access to all of the data to everyone, right? You might want to provide access to specific sets of data to specific people, handle multi-tenancy because different gateways may belong to different tenants. So how do you handle multi-tenancy? So between Prometheus, Thanos, and Observatorium project, there are a lot of open source projects there that you can leverage for some of this standardization. And those are some of the things that we practice.
So interestingly, these are still limited to the cloud native world. If you talk about the network vendor, again, the protocols are
increasingly, a lot of the network vendors are supporting Prometheus, right? So they expose their metrics in a Prometheus format. So I've been working in the 5G space the last couple of years. You'd be surprised. So every 5G vendor today is exposing metrics in a Prometheus-based format, and these are all like 5G core, RAN related metrics. They are all being exposed in a Prometheus format. So Prometheus is largely becoming de facto even in the networking world. The hardware boxes are still not there, but once you get to the SDN space, increasingly Prometheus is being used.
And again, like Prometheus is not designed to be that efficient in terms of the amount of light that it transfers.
You'll have to be careful in the usage, right? So if you are using, so let's say you are dependent on metrics that you need to respond to within, let's say, a few tens of milliseconds, Prometheus is not the right approach because it uses a pull-based technology, right? Every time period it's going to scrape metrics, right? Whereas if you are really interested in real-time response, you might want to go for a push-based technology. There are multiple products that have a push-based metric monitoring system. So for all of your real-time use cases, I think the push-based method is better. For the the near real-time, non-real-time sort of use cases, where all you want to do, like the primary sort of use cases are where you want to collect data over, let's say, tens of minutes or even hours, and then respond, right? For those, or you want to provide a unified dashboard for everything that's going on across the world, Prometheus is becoming the one that's extremely scalable to tens of thousands of metrics and data points.
Agreed, but you also mentioned eBPF exporting to Prometheus, where your events are being generated at microsecond.
Correct. If you are, yes, right now that's, I think, good point. eBPF, we are not using it in the microsecond granularity that some others are doing. So if you are collecting metrics at a microsecond granularity, then it's best to use a different sort of technology and respond to it right in that same cluster itself, right? Instead, where we are is it's not even in the tens of milliseconds, right? We are in the hundreds of milliseconds to seconds granularity. That's the granularity at which we are collecting metrics here. So we are not looking at microsecond level. You can do it with eBPF. eBPF is very much capable of doing it. So we've even collected nanosecond scale system calls using eBPF. But those sort of use cases are different. And you shouldn't use Prometheus for when you're collecting nanosecond scale metrics. It's not really built for that. Okay, so maybe we should end it off here.
Thank you, Dr.
Thank you.
For the talk. The link to the slides will be posted on the web page. Thank you and have a great evening.
Thank you.